the you can see the diverging density state from the boundary singularity filling fractions. And if you actually plot the Fermi surface nesting from a Fermi surface structure from this boundary singularity, you can see that the Fermi surface of the kagome lattice actually forms this perfect hexagonal shape with the perfect nesting vector between the two parallel segments of the hexagons. So this indicates that this combination of the diverging density of state and the Fermi surface nesting can easily promote the various many-body orders, for example, like spin density wave and the charge density wave orders in the kagome lattice. And if you're willing to go one step further in theory, it is the boundary singularity in the kagome lattice is actually special because it has a definite sublattice character which changes as a function of momentum along this Fermi surface contour. So effect of this sublattice decoration on the Fermi surface is basically suppressing the on-site Coulomb interaction while enhancing the low of the non-local Coulomb interaction. So based on this sublattice decorated Fermi surface of the kagome lattice, one can in principle realize non-trivial many-body phases, for example, unconventional superconductivity or the chiral density wave phases. And there are also a lot of interesting theories about the boundary singularities in the hexagonal lattice and the kagome lattice system. So I again leave some of the references here. So at least theoretically, we now know that we can do many interesting things with the band structure of the kagome lattice. So then question is how we can actually experimentally realize this band structure of the kagome lattice in linear material system. So here I again compare this case with the case of the hexagonal lattice system. So the band structure of the hexagonal lattice or the physics of the hexagonal lattice has been realized from early 2000 in the graphene-based family of material. And this graphene family consists of the graphene, silicene, germanium, stannine, and so on. And these are mostly like very two-dimensional materials, so you can easily realize the Dirac point and Banach singularities arising from this hexagonal symmetry. However, there exists a lot of limitations in this compound. So for example, since the valence electronic structure in this compound arises from the PZ electron orbital character, this system has a very weak or negligible Coulomb interaction energy scale, and usually they feature no intrinsic magnetism. But more importantly, they have a very limited tunability in the electronic fillings because this family arises from the elements that comes from the same group in the same column in the periodic table. So for example, you can, even though there exists a Banach singularity in graphene, you cannot study the actual physics comes from the Banach singularity simply because you cannot fill the electrons to the Banach singularity levels. And in this context, the family of the material, the 3D transition metal-based kagome compounds that we have studied since 2017, has really overcome this a lot of limitations of the hexagonal lattice system, and really have a lot of distinct advantages in this context. So first, even though these materials are three-dimensional crystals, they have a relatively simple crystal structure or the unicell structure, so they still retains this band structure of the two-dimensional kagome lattice. For example, the Dirac electrons, Banach singularities, and flat band can be realized in this compound. And in contrast to the case of the hexagonal lattice system, the valence band electronic structure of this system comes from the 3D electrons of the transition metal atoms, so that this series of compounds feature various forms of the intrinsic magnetism, intrinsic spin of the coupling, and also it has a quite large Coulomb interaction energy scale arising from these 3D electrons. And I think the most important advantage of this series of material is that there is a large tunability in the electronic fillings. For example, by choosing appropriate transition metal atoms, you can basically tune your Fermi level from the Dirac point above the flat band, really depending on the physics that you want to investigate in this lattice band structure. So I think this large tunability in the electronic filling is a really important advantage of this class of materials. Sorry, I cannot hear you.
Can you hear me?
Yeah, I can hear you now.
Okay, good. I have a one short question. But is it known how to open the gap of the direct point for this kagome?
So in this, so for example, I guess your question is related to the fact that in case of the graphene, the spin-orbit coupling strength is negligible, like micro electron volt scale. So you cannot open a gap at the Dirac point. So as I have mentioned here, what I want to emphasize here is that in this 3D tensor metal-based kagome compounds, there is an intrinsic level of the spin-orbit coupling with like few tens of milli-electron volt scale. So your Dirac band will naturally have a spin-orbit coupling gap, unlike the case of the graphite. So I will discuss the experimental
So
data.
is that large enough to be useful?
I think so, yeah. For example, in one of the kagome compound that we have studied, iron 3 tin 2, there is the Dirac point is located at like 70 milli-electron volt binding energy, and the spin-orbit coupling gap is 30 milli-electron volt. So from that, you can have a very curvature effect even at the Fermi level.
Okay, thank you.
So as for the question, so I think what is most important and exciting is that during the past few years, we could actually realize almost all of this physics of the kagome lattice in their material system in various 3D tensor metal-based kagome compounds. For example, people have realized this Chern insulator phase in this iron 3 tin 2 and turbine mangan 16-6. People also realized this magnetic Bauer metal phase in mangan 3 tin, cobalt 3 tin 2 sulfur 2. And people realize, we realized the flat band induced strongly correlated phases in nickel 3 indium compound. And we also observed topological flat band in iron tin and cobalt tin. And people more recently discovered this alkali-metal vanadium timonite compound with the Banov singularity physics and also many-body electronic orderings. So among these many compounds, I would like to focus on this iron 3 tin 2, iron cobalt tin, nickel 3 indium, and alkali-metal vanadium timonite, which is our own study. So in the first part of my presentation, I would like to focus on this binary kagome metal series, TMXN. And most of this work has been done during my PhD in MIT in Ricardo Comin's group. And in this project, we really strongly collaborate with the Professor Drew Czekilski's group in MIT and with Dr. Rin Daye, who synthesized and measured the transport properties of this compound. And we have a lot of theory collaborators on this subject. So the main contributor is Dr. Xiang Fang from the Harvard University and Jeroen van den Brink's group in the IFW Dresden. But we are also collaborating with the Professor Bamjung Yang's group and Professor Jiun Shim's group in SNU and Postec on some of these materials. So please let me first introduce about the basic structure and the advantage of this material series. So this binary kagome metal compound has a composition, this TMXN, where T represents the transition metal atoms and the X represents the space filling atoms, which can be tin, germanium, or indium. And if you check the kagome layer of this compound, you can see that the kagome lattice network is constructed by the transition metal elements, and the X atoms basically fill the empty space at the center of the hexagon of the kagome lattice. And the reason why this material series is interesting is that by tuning the ratio of these transition metal atoms and space filling atoms, M to N, from 3 to 1 to 3 to 2 to 3 to 3 or 1 to 1, you can basically tune the stacking structure between the two kagome planes, and you can basically control the electronic dimensionality from fully 3-dimensional to 2-dimensional limit. For example, in this 3-1 compound, you can see that the neighboring kagome layers, marked with A and B here, are directly stacked with each other. So you expect a strong interlayer interaction and overall 3-dimensionality of the electronic structure. However, in the opposite limit in this 1-1 compound, you can see that the neighboring kagome planes are further separated by the additional space filling layers, so that you expect more 2-dimensional electronic structure localized at each kagome plane. And I want to briefly mention that this idea of controlling this electronic dimensionality by tuning the stacking sequence is actually very similar to the case of the famous case of the Rudelston-Popper series in the oxide compounds. So in this Rudelston-Popper series, it is widely known that you can tune the electronic dimensionality from fully 3-dimensional 113 structure to the most 2-dimensional 214 structure like cuprate and iridates based on the tuning this stacking sequence. And we basically apply the same idea to this binary kagome metal series. So in this sense, you can think this binary kagome metal series as a Rudelston-Popper series of the kagome metal. And the first compound that we have studied in this series is this iron 3 tin 2 compound, the 3-2 structure with the ferromagnetism at very high Curie temperature at like 670 Kelvin. And in this iron 3 tin 2 compound, by utilizing this angle dissolved photoemission spectroscopy measurements, we could directly reveal this beautiful linear dispersion with the Dirac point located at the K point. And this is actually very first observation of the theoretically proposed Dirac fermions arising from the kagome lattice symmetry in layer material. And unlike as the Professor Shin asked in previous question, unlike the case of the graphene, this iron-3 tint compound have some degree of the spin-off decoupling, like few tens of electron volt, arising from this iron 3D electronic degrees of freedom. So we expect some kind of spin-off decoupling effect at this Dirac point. And by analyzing the details, the second derivative plot and the energy distribution curve plot, you can actually see that there is a discontinuity at the Dirac point, which signals the opening of the spin-off decoupling gap of about 30 electron volt. So the band structure that we actually realized in this iron-3 tin2 compound is the spin polarized massive Dirac fermion spectrum arising from the intrinsic combination of the kagome lattice symmetry, spin-off decoupling, and intrinsic magnetism in this iron-3 tin2 compound. And this spin polarized massive Dirac electronic structure naturally acquires this Berry curvature based on the Haldane and K-Miller mechanism. And of course, this Haldane and K-Miller mechanism is originally based on the hexagonal lattice structure. But instead of the hexagonal lattice, which does not have any spin-off decoupling and magnetism, here we demonstrate that the very same physics can be realized on the kagome compound or 3D transition metal-based kagome compound, which features this intrinsic spin-off decoupling and intrinsic magnetism. And one of the distinct advantages of this iron-3 tin2 compound is that the Dirac point here is actually located very close to the Fermi level. So in iron-3 tin2, you can observe this characteristic 2 double Dirac cone spectrum, with the first Dirac point located at 70 electron volt binding energy, and the second Dirac point located at 180 electron volt binding energy. And considering the proximity of this 70 electron volt Dirac point to the Fermi level, you can actually expect that this Berry curvature from the massive Dirac electron will affect the transport properties at the Fermi level. And by actually measuring the transport properties, the 2D anomalous conductivity, we could actually confirm that there is an intrinsic anomalous conductivity of 0.27 is square over h. And we confirm that this directly arises from the Berry curvature of the massive Dirac fermion, but because it matches closely with our expectation, like 0.31 is square over h. So the significance of our study on this iron-3 tin2 compound is that we could realize the Dirac fermion arising from the kagome lattice symmetry for the first time, and we could also realize the Haldane physics, which really takes advantage of the intrinsic combination of the kagome lattice symmetry, spin-off decoupling, and magnetism in these 3D transition metal-based kagome compounds. And in this first study of this iron-3 tin2, we solely analyze all of our data based on the simple model of the two-dimensional kagome lattice. However, as I have mentioned earlier, this 3D structure actually have a very complex stacking sequence. So you really have to understand what is the role of the interlayer interaction and how it can affect the physics that we mentioned above. And again, the 3D structure have a two distinct kind of the stacking structure. So one is this ASA type stacking, where the center of the kagome plane in the neighboring kagome layers are identical to each other. And the other is this AB stacking, where the center of kagome plane shifts in the neighboring kagome plane. And the effect of this ASA stacking is basically the bonding antibonding type. So the interlayer interaction here just splits the Dirac band to 2 along the energy direction. So you can consider this as a bonding Dirac band, and you can consider this as an antibonding Dirac band. And this is basically the origin of this double Dirac cone structure that we observed in this RPS spectrum. And the effect of the second type of the interlayer stacking, the AB stacking, is breaking the C3 rotational symmetry due to this shift of the center of the kagome plane. And this breaking of C3 rotational symmetry means that your system does not have to confine your Dirac point at the K point. So this breaking of C3 rotational symmetry shifts the Dirac point to along the momentum space direction away from the K point. So you can actually see that the upper Dirac band located left side of the K point and the lower Dirac band located at the right side of the K point. And what we have found is that this shift in the momentum space actually depends on the KZ position that you prove. So the complete picture is that there is a winding of the Dirac node around the K point as a function of KZ. So this shows this winding of the Dirac point as a function of KZ. So the complete picture of the Dirac physics in this iron-3 tin2 compound is the ferromagnetic helical Dirac node line structure arising from this complex combination of the interlayer stacking between the kagome planes. So far we have looked at this iron-3 tin2 compound, which is a 3D structure, which is located at somewhere between two-dimensional and the three-dimensional limit. So now let's briefly take a look on what kind of physics that we can realize in this three-dimensional limit, this 3-1 compound with enhanced interlayer interaction between the common plane. So the physics of the iron 3tin2 can be basically understood as a physics of the quantum Hole insulating kagome layer with the two-dimensional massive Dirac electrons localized at each kagome layer. And if you stack this quantum Hole insulating kagome layer to third dimension, and if you consider the effect of the interlayer interaction, you can basically close this spin-orbit coupling gap along the KZ direction and reopen it, realizing these three-dimensional biopoints. And based on the degree of the interlayer interaction and the size of the exchange field in your model, you can realize this complex phase diagram. So you can understand this phase diagram as if you have a zero or negligible interlayer interaction, you realize this quantum Hole insulating physics with fully gapped Dirac spectrum. But as you increase this interlayer interaction, your system transforms to the three-dimensional bioseminar phase by the closing of the gap as a function of Kc. And this physics of the three-dimensional biomagnetic biofermions is indeed realized in this 3-1 compound, mangan-3tin, with the enhanced interlayer interaction. So this is not our own work. This is the work from Satoru Nakatsuji's group in Japan. So I will only briefly mention their result here. So in this mangan-3tin structure, they actually observed very three-dimensional dispersion with a lot of variation of the band structure as a function of Kz, which is consistent with the enhanced interlayer interaction. And in this system, by performing the DFT calculation, they could actually find the three-dimensional biopoints and associated Fermi surface arc very close to the Fermi level. And they actually confirmed the existence of the biopoints in this material based on the Kara anomaly or the intrinsic anomalous conductivity measurements. So we can also consider positioning this iron 3tin2 and mangan 3tin compound in this phase diagram. So you can basically understand that in this iron 3tin2 structure, the interlayer interaction is not strong enough. So all you have is this quantum Hole physics. But as you increase the interlayer interaction in this 3-1 structure, you can basically realize the bioseminar phase in this mangan 3tin material. So far we have discussed the realization of the biophysics and Dirac physics in this 3-1 and 3-2 structure. But the basic limitation of these two structures is that you cannot realize the flat band. You cannot observe any flat dispersion in this material, which is another important ingredient of the kagome band structure. And we suspected that basically the reason why we couldn't observe flat band in this system is that here the interlayer interaction is too strong and just too complex, so that it simply destroys the flat band dispersion arising from the two-dimensional kagome plane. So we decided to pursue searching for this flat band structure in this two-dimensional limit, 1-1 compound, which has the largest separation between these kagome planes and which could be expected to realize the most two-dimensional physics of the kagome lattice. So in the compound that we have studied, the cobaltine, which is a 1-1 structure and which is non-magnetic, we could actually realize this flat band structure arising from the kagome lattice symmetry for the first time. And this flat band in cobaltine, as you can see from this RPS data, is basically dispersionless along very large momentum space window. And you can also see that this flat band dispersion does not vary a lot as a function of Kz. And this really indicates that this flat band is a two-dimensional flat band localized at each kagome plane, as you expected from this 1-1 structure. And you can also compare this flat band energy scale with the other energy scales in this compound. For example, the dispersion of the flat band or the kinetic energy scale of the flat band is 0.15 electron volt across the whole three-dimensional Brillouin zone, which is almost 10 times smaller than the Dirac band energy scale arising from the same orbital character, and which is about 30 times smaller than the interaction energy scale, which is about 5 electron volt, typically in this cobalt 3D system. So in this sense, you can really see that in this flat band, for this flat band electrons, the interaction energy scale dominates the kinetic energy scale, similar to other flat band systems, for example, the twisted bilayer graphene system. And finally, you can also confirm the non-trivial topology of the flat band in cobaltine. For example, by focusing on the zone center at the gamma point, you can directly observe the dispersion of the flat band and the dispersion from the Dirac band, which quadratically touches with the flat band at the zone center gamma point. And if you analyze the detailed energy distribution curve here, you can see the clear spin-orbit coupling gap between the flat band and the direct band. And this closely matches with the expectation from the tight binding band calculation. And you can also calculate the associated topological quantity like spin barrier curvature here. So you can also see that the spin barrier curvature really concentrates near the gamma point where there is an opening between the flat band and the direct band. Spin-orbit coupling gap opening between the flat band and the direct band. So all in all, this cobaltine really represents the prototypical realization of the topological flat band arising from the kagome lattice symmetry. And here I also want to mention that in these cobaltine cases, every electronic dispersion is just simply explained by the basic DFT calculation level.
I'm sorry. So can I ask you a question?
Yep.
Can you go back? Or maybe here. So this flat band is a little bit separated from pyramid surface. So what is the way to for this material to demonstrate its flat band?
So I think that, so you're right that in this material there is a flat band. The flat band is located quite away from the Fermi level, like 200 and 300 millielectron volt away from the Fermi level. So people actually have tried some way to tune this flat band to the Fermi level. So one of the way is that you can tune the tin, you can replace this tin with the indium. And if you see the periodic table, replacing tin with the indium basically means hold opening the system. So you can actually hold up the system and you can move this to flat band to approach to the Fermi level. And there is a recent report from, I think, Okrich's group, who realized this indium doped cobaltine compound, and they could observe some kind of like magnetic exchange interaction arising from the flat band electrons. So I think here the physics of the flat band is that it can create the Stoner type magnetism if you move this flat band to the Fermi level, and if you increase the density of state at the Fermi level.
Then what happens to that flat band when Fermi surface approach it?
So I think again that is a very important question, but we haven't studied this cobaltine indium system, so we don't have any data about this ARPAS data about how the flat band evolves as a function of indium doping. But we do have other data which we tried the iron doping to the cobalt side, which is also the hole doping. So in that case, the flat band actually evolves in quite complicated manner. And I don't actually have a slide here, but from the cobaltine to iron tin, you can see that the flat band basically evolves non-monotonically. So to some iron doping, the flat band goes down in energy, but as you dope iron more and more, the flat band goes up and approaches the Fermi level. And we are still trying to understand that behavior of the flat band as a function of iron doping, but unfortunately, I don't include that slide in this presentation. Yeah.
Interesting. Okay, thank you.
So actually, I guess this slide is quite relevant to the Professor Shin's question. So again, I mentioned that in these cobaltine cases, you can reproduce this phenomenology simply based on the simple DFT calculation. But the situation is different for these iron tin cases, where we observe this unexpected flat band that cannot be reproduced by the simple DFT calculation. So again, in cobaltine, you observe this beautiful flat band at like 0.3 electron volt binding energy. And this flat band position is fully reproduced by the DFT calculation. But in case of this antiferromagnetic iron tin compound, the DFT expects this flat band to split to spin up and spin down flat band. So it predicts the spin up flat band at 0.5 electron volt binding energy and spin down flat band above the Fermi level at 0.5 electron volt binding energy, 0.5 electron volt above the Fermi level. But to our surprise, our ARPAS measurements on iron tin compound actually reveal the flat band at very different energy position at like 0.2 electron volt binding energy, which is very different from what DFT predicts. So what we have suspected in this case is that maybe we need better theoretical approach or more sophisticated theoretical approach that can deal with this local correlation more correctly, which can be important for the flat band electrons in this kagome system. So for these reasons, we decided to pursue the DMFT calculation in collaboration with Professor Ji-Yoon Shim's group in postdoc. So we first performed the DMFT calculation with the local exchange parameter J equals 0.8 electron volt, which is known to be standard for the iron compound. And even in this DMFT calculation, you can see that the bandwidth of the kagome bands is kind of normalized in this DMFT calculation due to the effect of the correlation. But still, you cannot find the flat band at the 0.2 electron volt binding energy. So here, the flat band is predicted at like -1 and 0.3 electron volt above the Fermi level. And this still does not match with the flat band we observed in the RPS. So what we later found out is that this flat band position is actually very sensitive to the local parameter J that you plug in this DMFT calculation. And you actually have to reduce this J value by a lot, more than half of the standard value, to 0.32 electron volt to capture the position of the flat band, which we observed in this RPS. And we also performed these scanning tunneling microscopy measurements to confirm the validity of this DMFT calculation. So in this case, this scanning tunneling microscopy study is really complementary to the RPS measurements because it can measure the density of state both above and below the Fermi level. So if you see the density of state below the Fermi level, you can see the clear peak in the STM measurements, which matches with the position of the flat band that we observed in these RPS measurements. And if you see the above the flat band, you can see the second peak of the density of state at the 160 electron volt binding, 160 electron volt energy. And this position of the peak really matches with the position of the flat band predicted in the DMFT calculation. So this combination of the RPS and the STM measurements really confirms the validity of this DMFT calculation with the reduced J parameter. However, in terms of the physics, there still exists a lot of open questions at this stage. For example, we have to understand why this iron tin compound strictly requires the DMFT calculation to capture the position of the flat band, while the flat band in cobalt tin is simply reproduced by the DFT calculation. And more importantly, we also have to understand why we have to reduce this J value to 0.8 from 0.8 to 0.32 to capture this position of the flat band. So these are our open questions at this stage. But what I also want to mention that we performed a single-site DMFT calculation here, but in principle, the eigenstate of the flat band in the kagome lattice is distributed in this inside this hexagon. So it actually covers the multiples of lattice site. So I believe that more proper choice of the impurity to describe the flat band in the kagome lattice in this case should be cluster type impurity, which covers more than one sublattice site. So we are actually considering performing the cluster DMFT calculation in future to better understand the physics of the flat band in the iron tin compound. And finally, I also want to mention our results on this nickel-3 indium compound very briefly. So the flat band in cobalt tin and iron tin is good to observe spectroscopically, but as Professor Shin asked in previous question, the limitation there was that the flat band is not located at the Fermi level. So you cannot directly observe the correlated electronic behavior that arises from the flat band in cobalt tin and iron tin. So you can ask what kind of correlated electronic behavior can actually happen when you place your kagome flat band in the Fermi level. So the part of that answer can be found in this nickel-3 indium study, where we could directly observe this non-Fermi liquid behavior arising from the partially filled flat band. So if we first focus on this cousin compound, nickel-3 tin compound, the DFT calculation predicts the flat band at 0.2 electron volt binding energy. And this flat band is closely reproduced in our RPS experiment. So our RPS directly confirms the existence of the flat band in this case of the material. And you can tune the position of this flat band to the Fermi level by hole doping the system. And especially by replacing this tin atom to the indium atom, you can actually exactly position this flat band to the Fermi level. And in this nickel-3 indium compound, we actually observe this correlated electronic behavior arising from the partially filled flat band, which is the non-Fermi liquid behavior. For example, you can see that the resistivity follows the T-linear behavior at the low temperature, deviating from the conventional T-square behavior from the Fermi liquid model. And you can also see that the C/T heat capacity deviates from the standard Fermi liquid behavior at the low temperature. So, and I also want to mention that this non-Fermi liquid behavior is really unique properties of this nickel-3 indium. So in this other kagome system that we have studied, iron-3 tin, iron tin, and cobalt tin, all you observe is just regular T-square behavior following the Fermi-Leakey theory. And this is consistent with the fact that the flat band in this compound is located away from the Fermi level. So by this comparison, we can indeed confirm that the non-Fermi-Leakey behavior in Niken 3 indium directly arises from the partially filled flat band, where the strong correlation between the flat band electrons dominates the transport properties at the low temperature. So please let me summarize the physics that we have realized in this series of binary common metals, TMXN. So here we continue the dimensionality of the crystals and the electronic structure from 3-dimensional to 2-dimensional, and you want to explore the physics that you want to realize.
Hi, can you go back one slide? Yeah, right. In this in nickel indium.
Yep.
Is there any reason why superconductivity is not there at low temperature?
Yeah, I think that's a great question, and that's something that we have to explore in future. So the observation of this non-Fermi-Leakey behavior indicates that there is usually some proximity to the quantum critical points near, and maybe there is some kind of superconductivity emerging from this quantum critical fluctuation pairing scenario. But so far we haven't observed the superconductivity in this nickel 3 indium system, but maybe we can try to tune the parameters like electronic fillings or the pressure, applying the pressure to further observe the phase space of this nickel 3 indium system, and we can try to search for the superconductivity at the low temperature. But I think that is really a good research direction to explore, because you observe the non-Fermi-Leakey behavior, you have to see whether there is any quantum critical point or the relevant superconductivity in the phase diagram. But I have to admit that we haven't looked for the a lot of phase space here. So we have tried the doping of the tin, but we haven't performed, for example, like pressure dependent or the strain dependent measurements here. Yeah.
Thank you.
So in this binary common metal series, in the most 3-dimensional limit 3-1 compound, people could realize the 3-dimensional magnetic biofermion physics, like in manganese 3 tin. And in this 3-2 compound, iron 3 tin 2, we could realize this 2-dimensional massive fermion and the associated intrinsic aromatic cell conductivity. And finally, in most 2-dimensional 1-1 compound, we could realize the flat band coming from the kagome lattice symmetry. So in this cobaltine compound, we observe this topological flat band, and in this iron tin compound, we observe this unexpected flat band, which emphasizes that it is really important to deal with local correlation correctly to describe the physics of the flat band in this system. And in my second part of my talk, I'd like to switch a gear a bit and would like to discuss a more recently discovered vanadium antimonide series of common metal, alkali metal vanadium antimonide. And I started investigating this compound after I joined Professor Jae-Won Park's group in PostTech. And some of these measurements has been done in the local synchrotron in Pohang lasers. And the samples come from the Stephan Wilson's group in University of California, Santa Barbara, who originally discovered this series. So as I have mentioned in the introduction, from this kagome lattice dispersion, we can try to realize both non-trivial topology and also the many-body electronic phases. And during the past few years, various forms of the theoretically proposed topological phases have been indeed experimentally realized in various iron, mangan, and cobalt-based kagome compounds. In contrast, the common metal that realized these many-body electronic phases has been elusive for a long time. And then very recently, in late December 2020, the Dr. Brendan Ortiz in University of California, Santa Barbara discovered this alkali metal vanadium antimonide series with the vanadium-based kagome network. And in this alkali metal vanadium antimonide compound, he observed that there coexists the charge order and superconductivity similar to many other strongly correlated systems. And this observation of the many-body orders in kagome compound really expand and open the new research direction in this kagome metal field. And during the past few years, people actually have observed that observe a lot of variety of these electronic orders in addition to the charge order and the superconductivity, which includes tri-border electronic nematicity and the time-level symmetry breaking loop current orders in this compound. And it will be impossible to review all the interesting physics observed in this series here, but here I would like to at least briefly mention a few things about charge order and the superconductivity in this compound, which have direct relevance to my presentation today. So one of the earliest evidence of the charge order in this compound comes from the scanning tunneling microscopy study, where compared to the normal state, you can clearly find the emergence of the new periodicity in the Lie space and the corresponding 2x2 superlattice peak in the Fourier transformed STM image. And if you actually consider the structure of the charge order in this two-dimensional kagome plane, you can see that there exist two types of the distortions compatible with this 2x2 periodicity. So one is this Tarov-David type distortion, and the other is this trihexagonal type distortion. And later, people found out that people performed these hard X-ray diffraction measurements, and they measured the three-dimensional periodicity of the charge order in this sample. And they actually revealed that the charge order in this compound is a three-dimensional with the 2x2x2 modulation. So there is also modulation along the Z direction. Then, depending on the relative arrangement of the charge patterns in the neighboring kagome planes, various forms of the three-dimensional charge order structure can be realized in this compound. However, the exact structure of the three-dimensional charge order in this compound has not been fully discovered, fully revealed yet. So the exact structure of the charge order is still unknown in this compound. And if you go to the temperature far below the charge order transition temperature, the system undergoes the transition to the superconducting ground state. And one of the most intriguing features about the superconductivity in this system is the emergence of this double dome superconductivity, which is first observed in this pressure-dependent phase diagram, but later also in this thin doping-dependent phase diagram. And the maximum of the second superconducting dome seems to be correlated with the suppression of the charge order transition temperature to 0 Kelvin. But the origin of this complex evolution of TC inside this charge order phase is unknown at this stage. So this is still an open question. So in this alkali metal vanadium antimonide compound, the question that we would like to address is, what is the origin of all these interesting many-body phenomena observed in this kagome metal series? And since we have been focusing on this electronic structure of the kagome series, we want to know whether there is any correlation between the charge order and superconductivity in this compound and the underlying kagome electronic structure. So as I mentioned—
Can I ask you a question? Okay. So I think that any kagome has a Van Hoff singularity in principle.
That's true, yeah.
And what is the reason of this 135 type? Only that is showing this charge density wave.
So, yeah, I think that is a good question. So in the previous slide, I have mentioned that it is really important to tune the electronic filling in this kagome band structure to really observe the physics that you want to observe. So in this scission vanadium antimonide compound, the Van Hoff singularity filling fraction is really at the Fermi level. So in the other compound like cobalt-tin and iron-tin compound, even though Van Hoff singularity exists in the dispersion, it just does not locate at the Fermi level. So in this context, the scission vanadium antimonide is special and hosts charge density wave because there is a Van Hoff singularity at the Fermi level. And there also exists, more recently, people discovered the other kagome compounds, kagome metal series, that also have a similar charge density wave structure. So one of them is yttrium, chromium, germanium compound. So in this case, people also observed the similar charge order structure. So scission vanadium antimonide is not really unique compound exhibiting the charge density wave phase.
All right. And also, I mean, about this charge density wave origin, and it seems that you are saying that just nesting is the origin, while some people is disagreeing. And can you summarize what is the basic point of other people?
So I think I have a slide here. So I think the biggest claim from the group of people who believe that this charge density waves comes from the structural transition is that if you calculate the phonon spectrum from the normal state of this alkali metal vanadium antimonide series, you can see this unstable phonon modes in the normal state. So this usually indicates that the structure itself is unstable, and you can expect some kind of structural distortion at this below some temperature, right? So I think this is the reason that why some people believe that there is a dominant structural contribution that's driving these 2x2 distortions.
But I guess that it seems that you are saying that such a deformation itself can be considered as a charge order, right?
That's right, yeah. And the reason that it can be considered as a charge order is that it is such a weak distortion. So if you measure like a Bragg diffraction that comes from these charge order peaks, it's like 10 to the minus 6 order of strength for the normal Bragg. So I think that is the reason that we are considering this as from the charge order picture instead of the simple
The thing
structure.
I didn't understand was not by you, I mean, not for you, I mean, from other people was, I mean, such a lattice deformation itself is a consequence, not the origin or the region, right?
Yeah, that's right. Yeah. So I think so. People also calculated this frequency of this unstable phonon mode as a function of like electron fillings and also as a function of this electronic temperature. So that's the kind of parameter that they input in the DFT calculation that consider the broadening at the Fermi level. And they actually reveal that this frequency of these unstable phonon modes are actually very sensitive to the electronic part of this alkaline metal vanadium antimonide compound. So that means that this instability of the phonon itself is actually contributed by the electronic degrees of freedom. So considering that, I think it is important to consider the electronic part to understand this 2x2 distortion.
Okay, let's go.
Yeah. So thanks again for the question. And so here we basically consider these bound-up singularity scenarios to explain this 2x2 charge order. And I have mentioned that in the introduction that combination of the diverging density of state and the Fermi surface nesting can actually drive these many-body orders like charge density wave and spin density. And the nesting size of the nesting wave vector in this hexagonal Fermi surface is actually consistent with the periodicity of the 2x2 charge order in alkaline metal vanadium antimonide. And there is actually a very interesting theory about this bound-up singularity in the Kolmogorov lattice, which is the fact that there exists two distinct types of the bound-up singularity in this band dispersion. And these two types of the bound-up singularity arise from the intrinsic asymmetry of this Kalman band dispersion with respect to the Dirac band. So due to the presence of the flat band here, the Kalman lattice dispersion is not symmetric with respect to the Dirac band. So the wave function at these two bound-up singularities are distinguished. So these two distinctive bound-up singularity of the Kalman lattice are called P and M type bound-up singularities respectively. And the way to distinguish these two bound-up singularities are first by looking at their concavity. For example, this P-type bound-up singularity have a hole-like dispersion along K and K, and the electron-like dispersion along gamma and gamma direction, but the concavity becomes opposite for this M-type bound-up singularity. But what is more important is actually their sublattice character. So this P-type bound-up singularity have a pure sublattice character at the endpoint, while this M-type bound-up singularity have a mixed sublattice character at the endpoint. And I have mentioned that this sublattice character is important in determining the importance of the non-local Coulomb interaction and the momentum-dependent pairing. And even though the Fermi surface look exactly identical in these two bound-up singularities, the dominant instabilities that arise from the Fermi surface is actually very different for these two bound-up singularities. And these bound-up singularities can be a source of exotic density wave and also the Schottky activity. So we want to know whether this bound-up singularity physics is actually realized in this alkaline metal vanadium antimonide compound. So we actually investigated this vanadium antimonide compound with RPS, and we actually see the existence of multiple bound-up singularities near the Fermi level of this compound. And I think the best ways to visualize this bound-up singularity is by presenting the series of energy momentum dispersion measured perpendicular to this KMK direction. So here, COD 1 crosses the K point, and the COD 5 crosses the M point along the high symmetry gamma and gamma direction. So if you first focus on this COD 1, you can see the Dirac band at the K point arises from the DXZ and DYZ orbital degrees of freedom, and we'll call this band as a K2 band. And as you approach to the M point, you can see that this linear dispersion transforms to the quadratic band, and with this band bottom moving up in energy to the M point. So in this sense, you can confirm that this K2 band have a hole-like dispersion along the KMK direction. In contrast, along the gamma and gamma direction, this band still retains the electron-like character. So in this sense, you can directly confirm the existence of this saddle point dispersion or bound-up singularity, which have an electron-like dispersion along one direction and the hole-like dispersion along the perpendicular direction. And from this concavity, you can confirm that the K2 band has a p-type bound of singularity. And you can also calculate from the density of state that it has a pure sublattice character. And you can also perform the similar analysis on the K1 band, arises from the dx square minus y square orbital character. And you can also confirm that there exists similar bound of singularity near the Fermi level, which is also the p-type bound of singularity. And the situation is very different for this K2 prime band. So K2 prime band starts with the whole-like dispersion at the K point, and its band top moves down in energy as you approach to the M point. So this K2 prime band has an electron-like dispersion along the KMK, but it still retains the whole-like dispersion along the gamma and gamma direction. So in this sense, you can again confirm that bound of singularity exists near the Fermi level, but this bound of singularity has an M-type dispersion judging from concavity and also based on their sublattice projection from the DFT calculation. So if you summarize this part of the presentation, we could find 3 bound of singularities coexisting near the Fermi level of Sijun-Vanadium antimonide, and 2 of them has a p-type character, and one of them has an m-type character. And we can also directly confirm this law of the bound of singularities in this compound. So for example, if you look at this m-type K2 prime bound of singularity, and if you look at the Fermi surface, you can see that this K2 prime bound of singularity forms a almost perfect hexagonal Fermi surface with the nesting vector compatible with the 2x2 charge order. And you can directly contribute this Fermi surface nesting by observing the charge order gap at the low temperature. So if you go below the charge order transition temperature, you can see that there opens the charge order gaps along the nested part of the Fermi surface, which directly indicates that this Fermi surface nesting contributes to the electronic energy lowering in the charge order state. And you can also observe the similar band normalization from the K1 bound of singularity. So this p-type K1 bound of singularity has a whole-like dispersion along the KMK direction. And this whole-like dispersion becomes strongly normalized as you move down in temperature below the charge order temperature. So this band actually develops this characteristic M-shaped dispersion at the lowest temperature. And this indicates that the largest charge order gaps opens at the M point or at the bound of singularity. And this directly indicates that the large density of state from the bound of singularity directly contributes to the electronic energy lowering in the charge order state. So from our study, we suggest that there is a close connection between this unique bound of singularity physics of the Kagome lattice and various unconventional many-body ordering in Sijun-Vanadium antimonide. So we basically want to propose that we have to start understanding this various kind of many-body orders, starting from this bound of singularity physics of the Kagome lattice. And during the final 3 minutes of my presentation, I would like to briefly publicize our more recent work, which we consider the detailed microscopic structure of the 3-dimensional charge order in this compound. So in this compound, I mentioned that people still don't understand the exact structure of the 3-dimensional charge order. And here we developed a methodology to constrain or determine this 3-dimensional charge order structure by looking at the detailed energy momentum dispersion in this 3-dimensional charge order. So this 3-dimensional charge order structure imposes different types of the interlayer and different types of the intra-layer interaction, so that they actually reconstruct the Kagome bands in very different manner. For example, this LLL charge order structure splits this lower Dirac band to 2, while this in this MLL charge order structure, these Dirac bands remain as a single line. So in this sense, you can basically distinguish this 3D charge order structure by looking at the details of the electronic band dispersion. And this analysis or determination of this 3-dimensional charge order structure actually allows to identify the origin of this double dome superconductivity. So here we studied the evolution of this 3-dimensional charge order structure as a function of tin doping in this Sijun-Vanadium antimonide compound. So you can see that in Sijun-Vanadium antimonide, the K1 lower Dirac band clearly splits to 2, which indicates that it has this LLL type charge order structure. And the splitting of this lower Dirac band persists to the 3% tin doped sample, but in the 4% tin doped sample, the splitting suddenly disappears. This indicates that there is a transition of the charge order structure from the LLL phase at the low tin concentration to the MLL phase at the higher tin concentration. So if we overlay this transition on top of the phase diagram of the superconducting phase diagram, you can see that there is this transition between the two 3-dimensional charge order structure actually coincides with the maximum of the first superconducting dome. So from this, our explanation of this double dome superconductivity is that the competition between charge order and superconductivity in this compound is strongly dependent on the three-dimensional charge order structure. And especially we suspect that this MLO's 3D charge order structure competes more strongly with the superconductivity, suppressing the TC in this intermediate tin concentration. And this in the end results in this double dome superconductivity. And from the understanding of this microscopic structure of the 3D charge order, we can also understand the material dependent superconducting critical temperature in this alkaline metal vanadium antimonide series. So if you see the superconducting TC in this potassium rubidium cesium compound, you can see that the TC of potassium and rubidium compound is much lower than 2.5 Kelvin of cesium vanadium antimonide. And we can also explain this by determining the different 3D charge order structure at each compound. And again, this ML charge order seems to more strongly compete with the superconductivity, suppressing the TC in this potassium and rubidium compound. So our study indicates that it is really important to understand the detailed microscopic structure of the three-dimensional charge order to really understand the many-body phenomena in this system, like superconducting phenomenology. So with this, I'd like to conclude my presentation with this slide. So in the first part of our research, we have studied these binary kagome metals where we could study this Dirac and flat band physics. And at the 2020, more recently, people discovered this vanadium antimonide series, which realized this Banach singularity physics, and people observe many different kind of many-body phenomena in this system. And we are also actively looking for another kagome quantum matter system, which can expand and develop this research direction to the new direction. So with this, I'd like to thank for your attention.
Thank you. Are there any questions?
Yeah. Can I have a question?
Yes.
The CVS, you mentioned there might be some correlation between the CDW order and the pair density wave order.
So I haven't between the CDW and pair density wave.
Yeah. Is that what you were pointing at?
No, I was saying that maybe the origin of this all interesting many-body phenomena may be from the Banach singularity. So we may understand this emergent many-body phenomena based on the Banach singularity physics of the kagome lattice. So I haven't mentioned any specifics about the pair density.
Wait. No, but on the right-hand side, you say pair density wave.
Yeah, that's true. Yeah. But I'm not claiming any correlation between the pair density wave and the charge density wave in this component.
But you're saying the Banach singularity is responsible for all of these many-body phenomena.
Yeah, I'm suspecting that, but maybe not the superconductivity, because it seems like the superconductivity is competing with the charge density wave. So if the charge density wave comes from the Banach singularity and it gaps out the R Fermi surface a portion, then the superconductivity cannot originate from the Banach singularity. So maybe the superconductivity is not relevant to the Banach singularity.
All right. Okay.
Any other question? If not, let's thank the speaker again.
Thank you very much.
And thank you very much for joining us and giving a very interesting talk. So I wish maybe you can come down APCTP when you are free.
Yeah,
I'm
I'm actually at Postec, so yeah, I'm basically right next building. Yeah. So.
Okay. So I expect to see you sometime.
Yeah. Okay. Yeah, that would be great. Yeah.
Okay. Bye bye.